Welcome to the second of the three videos. Here we'll be discussing distributions, their mean, mode, median, variance, PMFs, PDFs, CDFs, etc. Now, it's very likely that you will only deal directly with distributions and not with, sample spaces and events. Now, for discrete measures P, right? So where there are only a discrete number of outcomes, a finite number or an infinite number, but they're discrete, say, then it is enough to keep track of just the singletons P of omega I for each such singleton set. And this is a probability mass function. So for the coin example, it's just enough to know what is the probability of heads and what is the probability of tails. Similarly, in the dice example, it's enough just to know the probability of a 1 or a 2 or a 3 or a 4 or a 5 or a 6 individually, just as singletons. That tells you everything about the discrete measure P. For continuous measures, the story is slightly different. It is enough to keep track of P probability that x is less than equal to t. So remember, for a continuous measure, the outcomes have to be continuous, and x is a random variable, and you can ask what is the probability that the random variable takes on values less than equal to t. And remember again that when we say x less than equal to t, we really mean omega, such that x of omega is less than equal to t. Right? So we really, over here, we mean p of omega such that x of omega is less than equal to t. And that's just nothing but omega is a subset of x inverse of minus infinity to t. So that is x of omega is less than t. X of omega, that is the same thing as saying that x of omega is in minus infinity comma t. And so omega is in x inverse of minus infinity comma t. And so if we keep track of just these quantities, p of x less than equal to t, that's called a cumulative distribution function. It's often called capital F of t. It's the cumulative distribution function of this random variable x. Remember that I can assign like x values, real values according to the outcomes however I want, in which case the cumulative distribution function will change. So for the coin example, if capital X took on values minus 2 and 2, then the probability mass function would be different from when it took on values minus 1 and 1. And similarly, if I measured X in hours instead of seconds for the amount of time you waited for a bus, then the cumulative distribution function will look different. And those would be two different random variables. Now, if there is an f, if there is a little f, such that this probability x less than equal to t can be written as the integral from minus infinity to x f of x dx. If this is the case, then f of x is called the PDF, or the probability distribution function of the random variable. And it's important to remember that f of x is not the probability that x is equal to x. In fact, for a continuous random variable, the probability that capital X is equal to any particular value is always 0. And so you should never interpret the PDF as telling you what is the probability of getting that particular value. It's not. The only way of interpreting the PDF is that the probability say that b less than equal to x is less than equal to a can then be given as the integral from a to b of f of x dx. That these two quantities would be the same. That's the only way to wonder what does f of x tell me. It tells me the probability that that x say lies in an interval, or a union of disjoint intervals or something like that, by calculating integrals. It cannot be interpreted like this directly. That's all we have to say for the moment about distributions and random variables and events. Next time we'll continue by talking about means and variances and moments and things of that sort. Let us look at how we pictorially represent the PMF, CDF and PDF. So for a probability mass function, assume that this is the domain X, and suppose at X equal to 0 we assign a probability of half, and for X equal to 1 we assign a probability of half. Then this is how we represent the PMF, right? So it's just probability associated with a particular X, right? So this would be the example of the coin tossing thing where both of these values are 0.5. Of course, in a different setting, if there were more discrete values, what you'd find is that some of them were larger, some of them were smaller, and they don't even have to be evenly spaced or anything like that. So this would be another valid PMF as long as these quantities are positive and sum to 1. Now, actually, a PMF and a PDF can both be described by the CDF. The CDF, if you remember, that is f of t, is the probability that x is less than equal to t. Now, the CDF has to satisfy certain basic properties. One of them is that at minus infinity, the value should be 0, and at plus infinity, the value should be 1. So typically, a CDF is going to look something like that, where this is the value 1 that it saturates at, and this is the value 0, of course. And at minus infinity, it has to be 0 because the probability that x is less than minus infinity intuitively that has to be 0. And again, the probability that x is less than plus infinity intuitively has to be 1. For a discrete distribution, things would look slightly different. For discrete distribution, the CDF would be a series of jumps. The value at a particular point would be given by the larger one. The larger quantity is the actual value assigned to the point. And I mean, the interpretation again in this case also is very simple. Of course, it saturates at 1. When I'm looking at a PMF, I'm asking how much probability is to the left of this point, or to the left of this point, or to the left of this point, and so on. So for every point in the space, I'm asking what is the probability that x is less than equal to that point. Firstly, it has to be 0 at minus infinity and 1 at plus infinity, but also it has to be right continuous. So when I approach it from the right, the value at that point is actually achieved by the sequence that approaches that point. Thirdly, it has to be increasing, so it always has to increase because I'm never adding any negative quantities, and so it's a non-decreasing function. So the CDF is any non-decreasing function that satisfies those 4 properties. That is, f at minus infinity is 0, f at plus infinity is 1, and then it is non-decreasing. It's non-decreasing, and it is right continuous. Right continuous. Right. So any function satisfying these 4 properties is a valid CDF. Now the PDF is the continuous version of what's going on here. It's here's an example of a PDF. Just the same way as a PMF has to sum to 1, a PDF has to integrate to 1. So you'll often see people writing integral p of x dx is equal to 1. So that when we write an integral, as we discussed in the earlier chapters, earlier tutorials, if we write an integral without really specifying the limits, it's often understood to be the domain of p. And in this case, that would be something like minus infinity to infinity. But sometimes people will just drop the limits, but you should understand what that means. And again, as I mentioned earlier, the interpretation of the probability distribution function is not the probability of observing that value. The only way to interpret it is that if I um, integrate the PDF between A and B, I'm going to get some number between 0 and 1. Of course, if I integrate from minus infinity to infinity, I get 1. So if I integrate over a smaller interval, I'm going to get a smaller value like 0.3. And that tells me the probability that my random variable will fall between A and B. So if integral f of x, f, I can use f or p, I mean, you can use whatever notation you want. But if integral f of x from a to b is 0.3, then the probability that a less than equal to x less than equal to b is 0.3. That's how we interpret the PDF. Again, the PDF can be described by such a continuous CDF, which describes the probability of x less than equal to some point. That's what it would be. So if I'm looking at t, then this is the value here is the probability that x is less than equal to t, which is the integral from minus infinity to t of f of x dx. Right? So this value is just integral from minus infinity to t f of x dx. Right? And that's how the PDF and the CDF are related to each other. Let's move on. There are three important central points of a distribution, if you might. The median is the point at which f of t crosses 0.5, or rather it's the point where the probability of being less than equal to that point is the same as the probability of being larger than that point. That's the median. The mode is the point where either the PMF or the PDF is maximum. So in the previous example, that is the mode of the PDF, and the largest peak would be the mode of the PMF. The mean of a random variable x is the average value of x of omega when the probability of observing a particular omega is given by the underlying probability measure. Right? So it's the average value of this x of omega. Example for a coin, the expected value of x is 1 with, you observe 1 with a probability of x being 1, and you observe 0 with a probability of x being 0, and both of these are 0.5 for an unbiased coin, so I just get 1 times 0.5, which is 0.5. Right? So it's basically just I take a weighted average of all my points. So if I can observe 1 with some probability, 0 with some probability, and minus 1 with some other probability, then I would be just taking a weighted summation of all of those values. For continuous variables, of course, the weighted average becomes an integral. So here you're taking an integral. These are the values, so it's an integral of x. Instead of p of x equal to 1, you have f of x dx. So it's the integral of x f of x dx. Of course, the integral of f of x dx itself is 1. So this f of x really acts like a weighting function. So that's why it's like a weighted average of the different values that x takes. And again, when I write this integral, it's understood to mean the integral over the domain of x. And so you might understand it to be just minus infinity to infinity, as long as everything makes sense. You needn't just be able to take an expectation of a random variable. So an expectation is the mean, it's the same thing. But you can even take expectations of functions of random variables. So the expectation of g of x is just given by integral g of x f of x dx. If g of x is x, then it's integral x f of x dx. But this is the more general way of thinking about it. And finally, we can define the variance. And the variance is just the expected value of x minus its mean the whole squared. So this is some function of x, right? That function of x is x minus its mean the whole squared, right? So that's the definition. And One way to think about the variance is basically how much does the random variable really vary. So, for example, something like that would have a much larger variance than that. So, if I'm drawing PDFs, then this is saying that maybe most of the probability of observing the random variable lies in this region, right? So maybe if I integrated it, then this region would have a total probability of zero point 0.9, which means with a zero point 0.9 probability I'll observe a very small dispersion of values. But it's possible that maybe if I integrated between here and here, then I'd only get 0 0.5, and maybe I'd have to integrate between here and here to get 0 point 0.9. So that would mean that with probability 0 point 0.9 I can get any value in this region. So of course this random variable varies much more than this random variable, and that's captured exactly by the variance. The variance of this distribution will be small and the variance of this distribution will be large.